ordinary generating function of Stirling number of first kind. Okay guys, if you do not know about the Stirling number of first kind, in the previous video I just gave a one-on-one intro session to that number, and then also I sort of derived the recurrence relation for that number, right? So I'm not gonna do that again, so I will just link my previous video in the description. In the previous video, I was actually trying to solve another problem, but like before I went into problem, I feel like I should like give some intro, right? But since I already did that over there, so I'm gonna repeat that. So the link is in the description. Do check if you do not know about this number. But yeah, if you know that and if you know the recurrence relation, we are good to begin. Okay, this thing, the Stirling number of second kind, basically satisfies the relation, right? And it's noted by this big square bracket or like rectangle bracket, right? And the recurrence relation that it satisfies is n minus 1 k plus n minus 1 k minus 1, right? Using this, we actually have to derive this formula. So what I'm going to do is I'm going to first of all multiply all the sides with x to the power k, right? This is basically the recurrence relation for Stirling number of first kind. And also it's unsigned. There are different two types like signed and unsigned. This one is unsigned. Okay, so first of all, let's just put x to the power k, multiply the whole expression by x to the power k, right? And after that, we are gonna sum it up from k equals to 0 to n. This whole thing from k equals to 0 to n. Okay, so it becomes sum from k equals to 0 to n of Stirling number of first kind and k x to the power k is equals, now n mention is just constant in the sum if the sum is in the world of k, right? And then n minus 1 k x to the power k plus sum from k equals to 0 to n, and then n minus 1 k minus 1 x to the power k, right? Okay, now to do the sum, let us just define the sum from n equals to sum from k equals to 0 to n of n k x to the power k to be f of n comma x, right? Let's just define that and we'll try to solve for this function. Okay, now this becomes f of n comma x, right? And this will be equals to n minus 1. Now I can actually write the sum from k equals to 0 to n minus 1 because at n we'll just have n minus 1 Stirling first kind n, right? So it k equals to n, this will just be n minus 1 with n, right? And this will be 0 because whenever k is greater than n, we just consider n k to be 0. So from there, this will just be 0 at k equals to n. So that's why we can actually write the sum from k equals to 0 to n minus 1. And then n minus 1 k, right? But here also when k is 0, this is n minus 1 minus 1, right? And that's also defined to be 0 because like it's not really possible from the definition of the first kind. The definition is actually the number of permutations that you can make, but like it's not really possible to make permutation with n minus 1 elements, so it's just minus 1 elements, so that's defined to be 0. So what you can do, you can actually let this go from 1 because at 1 this is n minus 1 0 and that's defined, and then n minus 1 k minus 1 x to the power k. Okay, now again note that if we substitute n minus 1 over here, this f of n minus 1 x is just sum from k equals to 0 to n minus 1 k x to the power k, right? So this is the same thing that we have over here. So that becomes f of n comma x is equals to n minus 1 f of n minus 1 comma x. Now this one also we can write it as sum going from k equals to 0 to n minus 1 and increase all the k's. So this k and this becomes k plus 1, right? So now we have f of n comma x as n minus 1 f of n minus 1 comma x plus this becomes x times f of n minus 1 comma x, right? Yeah. So this is f of n comma x is equals to, if I take f of n minus 1 comma x common, I will have x plus n minus 1, right? Okay, and that's a good recurrence relation. Now from here you might be able to find out that if we substitute n as 1, right? If we substitute n as 1 over here, you get f of, actually let's use this one. Okay, over here if we substitute n as 0, f of 0 comma x will just be sum from k equals to 0 to 0, right? And then you will have 0k and then x to the power k, right? Okay, and now at 0, 0, 0 starting of first kind 0, that's just 1, and x to the power 0 is also 1, so this actually becomes just 1, right? Okay, so from there we now see that if you want to find 1 comma x, that's just f of 0 comma x into x plus 1 minus 1, which is x, right? F of 0 comma x is just 1, so 1 into x, which is x, right? Yeah. Okay, now f of 2 comma x is just f of 1 comma x into x plus 2 minus 1, which is x plus 1, right? So this is x times x plus 1. Okay, nice. Now f of 3 comma x is equals to, this is f of 2 comma x into, now this is x plus 3 minus 1, which is x plus 2, right? So this becomes um x, x plus 1, x plus 2, right? Similarly, f 4 plus x will just be x, x plus 1, x plus 2, x plus 3, right? So basically, whenever there's number n over here, it's just n plus 1. Sorry, x plus, okay, up to, it goes up to n minus 1. Yeah, you see the pattern, right? So that's the, okay, this is actually product, not intro. Okay, so that's actually pattern. You can prove this using induction, right? Because after you have the base case, this base case over here, if you have this base case and this recurrence, using induction you can actually prove that this is the correct formula, right? And yeah, so there are like basically n terms over here, so this is actually defined as rising factorial, so this is x to the power rising factorial, and so that's how it's defined, and that's the answer, right? Also, let me tell you, like, this rising factorial is actually x, x plus 1, there should be n terms over here. This also, okay, this is, guys, I'm sorry, this is not rising factorial, that's falling factorial. Rising factorial is like this. Yeah. And this falling factorial, this is x, x minus 1, x minus 2, up to x minus n plus 1. Okay, please do know about these two things, the rising factorial and falling factorial, those are helpful, right? Yeah. Like falling factorial, if it's like uh, x to the power 1, if it's a falling factorial of 1, then that's just uh, x factorial, right? But for the numbers, this is also helpful, this is also helpful, okay? So yeah, so we see that this function is actually the rising factorial, right? And that's what we wanted to prove. We wanted to prove that this function over here is just x to the power rising factorial, and yeah. Damn it, why do I always write falling factorial when I'm trying to write rising factorial? Okay, rising factorial. Rising factorial, yeah, good. Rising factorial, good, okay. So we have proved this thing, and that is it for now. In the next videos, maybe I'll come up with some other interesting generating function of the Stirling numbers. Yeah, let's do quite a few videos on these numbers because these are some interesting numbers. And then we'll proceed ahead into other contents. Thanks for watching. I look forward to seeing you in the upcoming videos too.